play with a data set that has a numerical interaction. But I'm going to warn you right from the start, it's going to take us a while to get to where we can do the interaction, and then we'll in the next video actually see how to explain it. The data set we want to play with is called brain function, and it has more column than column names. Well, this is one of those data sets that has a whole bunch of text at the beginning telling you what's what. Now, brain is what we want to predict. It's the brain function, some percentage of neuron firing, because as we all know, we only use half of our brain, or so they say. Hours is the number of hours you work, and age is the age of the subject. So I need to skip 1, 2, 3. Let's skip the first 4 lines. So at the end here, I'm going to add my skip equals 4. Give me brains. We got brain. I'm going to sound like a zombie at the end of this. Brain. Let's plot brain. Okay, brain is what we want to predict. And if we look at the plot of brain versus hour, we see that triangle shape. Brain not found. Oh, I'm going to have a problem here because I've named my data set brain, and brain is also one of the things in my data. So I can fix that if I call this brain data, and that way when I'm plotting brain data, and brain all by itself is now the variable in the brain data, just trying not to get myself confused. And there is our triangle shape. Of course, I think I'm going to say remove that dataset brain that I created before. Okay, good. Now, that triangle shape, it looks like we could do a linear regression here. We're going to have an issue of non-constant variance. But as you saw in the last movie, this triangle shape is actually a clue that maybe what we're seeing is a straight line that's bending down as it goes along. Especially since if I do the same plot on age, I see a similar pattern. 2 variables that are having similar patterns makes me think there might be an interaction going on. But let's pretend I didn't know that. And I'm going to make a fit that has age and hours, but they're not multiplied together. Now you might say to yourself, why don't we always just multiply everything? Well, eventually we're going to get to where we can work with 10 or 20 variables. Multiplying all of them, that would be you'd be talking about a whole lot of interactions. So you don't necessarily want to throw in interactions at the beginning unless you see something like this triangle pattern that gives it away. So let's pretend we're just going to do our fit object, Brian not found, Brian. If there's anyone named Brian out there, I just called you a brainiac, so you should feel all happy about that. I'm going to plot these one by one because we want to look at our fits. Fit is not found because I didn't run it. Boy, see that curve? There's definitely something that needs to be fixed here. QQ plot's all right. We wish it was a little better in this area here. This is definitely showing some curvature. And a split here, like there's shadows happening. Of course, this is telling you which data points are influential, and some are influential one way, some are influential the other way, still hinting that there could be some interaction in there. But it might look just like curving to you based on this guy. So let's pretend that we think it's curving. And so we would put in age squared and hours squared. Let's see how that looks. My residual plot has the exact same curvature. There's curving happening, but it's not age that's curving, and it's not hours that's curving. The answer is going to be it's both. But as you look through here, we haven't improved anything. So now it's time for me to teach you a super valuable tool. I feel like hashtag power tool, supernova, atomic bomb. There should be some cool name for what we're about to do, but being able to look at the residuals by the variables will help you spot a lot of things that you can't see with this overall residual because you're looking at shadows overlaying shadows. So I'm going to make a plot. What do I want? I want my residuals. So I'm going to tell R, go into the box called fit. That's my regression box, right? It's got a ton of stuff in there. $, and look, here's all the stuff that's sitting in that box. And one of the things is residuals. So I can say, give me the fit $residuals and plot that against, now go into the brain data, which is a different box, right? We've got a box with brain data and a box with the regression output. So I've got to, since I'm digging out of 2 different boxes, I've got to call it by each box with the $. Brain data $, let's start with age and plot that. Ooh, and look at that. There's your classic bow tie. We're seeing some linear trend which starts here and then it slowly rotates. which is why it's giving us that. And that's a hint that there's a rotation or an interaction or an effect modifier going on somewhere. Who could it be interacting with? Well, it's not exactly rocket science at this point. There's only one other variable for it to interact with. That's hours. Does hours have a similar shape? Yes. We see residuals on age and on hours both have a similar shape. That's a big clue. So now we're ready to do what you probably guessed we were going to do from the beginning, which is we're going to have age and hours, but we're also going to have an age times hours. And it is true that because this is R, you can do a little cheat, and that will do the exact same thing. Let's take a look at our residual. Before we had this nasty curvature, and now, oh look, that looks beautiful except for this particular dot. And that looks really nice, except there's one person. And this looks great except one person. And look at leverage. Everybody seems to be following in line, except there's one person who's breaking the trend. Why couldn't we see that so strongly before? Well, we could a little bit. Here's the leverage plot we had before, and data point 900 was the furthest out there, but you couldn't even see the dashed lines. And suddenly now, if we go back, there's two dashed lines, and it's outside both of them. Why couldn't we see it before? Because there was this three-dimensional curving and a dot hidden inside, so that the shadow was making it not seem as important as it really was. So what is it about this data point? Well, it's not a big data set, and I warned you at the beginning of the video that we were going to have to spend some time trying to make this work the way we wanted, and that's because I knew 900 was going to do this. Let's find it right here. Okay, so data point 900. This is an 80-year-old who works 50 hours a week and has a brain function of 66.1. Okay, that might seem like a lot, but if we look at the data points, people who work 50 hours a week and have a brain function, I already forgot, brain function of 66.1, that's not unusual. There's our data point right there. What about 80-year-olds who work 66 hours? Let's see, brain function 66 for an 80-year-old. That's not unusual. There's something about both of those characteristics together that makes this one data point weird. An 80-year-old that works 50 hours a week. Well, let's take a look at age based on hours for 80-year-olds that work 50 hours a week. This is the very tip corner. These are the oldest and hardest working people. I'm going to call this data point the Betty White of our data points. Someone who's really old and still kicking out a massive amount of work. And just to make sure that this is our data point 900, I'm going to color it red. And look, we've got a red dot right there. So that's what makes this influential. This is the oldest, hardest working person. And what kind of brain function should they have? Well, I can run a predict.ln and say I want new data with an age of 80 and an hours of 50. And I don't know if you guys noticed this, but I got an error at first. And of course the video was paused, so I got away with it. It's because I capitalized prediction. Little things like that can take you a long time. Don't be frustrated. That's how it works. That's why people pay statisticians to do this. But we predict Betty White's brain function should be 2.1. The lower should be negative. This is a very old, hardworking person. It's kind of expected that their brain's not going to be functioning very well. The upper would be a 9.41. And for this Betty White, she's got a 66.1. She should not have a brain that is this fantastic, and yet it is. So that's why she's so influential. She really is an outlier, but her brain function is not outside of what's normal for humans. It's just outside of what's normal for people this old working this hard. So I'm having a hard time deciding, should I delete this one or not? Well, I can actually try it both ways, and that's actually how they calculate the leverage. Let's run a fit with no Betty White in it, and our brain function, it's the same model, but in our brain data, I want row 900 to be cut out of the data set when I run it. And how do my summary statistics look? Well, it's too hard to see all the output. So let me just grab the coefficients out of the regression box without Betty and the regression box with Betty. And you can see our intercept went from 96.23 without Betty to a 96.73 with. This 0.05 turned into a 0.06. 0.21 became a 0.18. So yeah, there's a difference. That's why this leverage plot put Betty clear out there, because with or without her, we do get a little bit of different numbers. Is it enough to say that Betty's ruining our analysis? Okay, I'm going to decide that Betty White is a legitimate person and that the fact that she's unusual makes her even more valuable to my data set. So I really do want her, and I want to keep her, which means I'm going to go back to my fit. I'm not going to use the fit no Betty. But you could argue or justify a different one as long as you're really clear about why you deleted the data points. We're not deleting the data points because we don't like them. We would delete the data points because she's not a good representative of a normal person. And if you want to try to make that justification, you can. I think now that I've called it Betty White, I'm already feeling an attachment to that data point. I think we're going to have to stick with it. Although, now that I have done the prediction for Betty, I really am curious, what would my brain function be? Well, let's see, I'm 37, and I work 45 hours a week. Oh, well, I should have 61% brain function. Not sure how I feel about that. I guess I'm just going to remind myself that it's made up data and we're not going to take this personally. The last step for this video is we look at a summary of our output, and here we have the effective age in hours and the interaction term age by hours. This is the modifier that's going to allow hours to modify age or age modify hours, depending on which way you're looking at it. My p-values are all significant, telling me that yes, that interaction really was important. My residuals now look nice, except for one data point, which I'm going to justify should stay in there. I think I'm ready to write up a report, which is what you'll see in the next video.